When wiring a commercial building, understanding conduit fill calculations is crucial, especially when dealing with three-way switches. The question arises whether to count all 3 wires for each three-way switch or only 2. The correct approach is to count only 2 of the 3 wires for each three-way switch when calculating conduit fill. In a three-way switch configuration, 2 current-carrying conductors exist. These are the traveler wires. The traveler wires carry the current between the switches and ultimately to the light fixture. The third wire, which is the common wire, is used only to complete the circuit when both switches are in the same position. Therefore, only the 2 traveler wires should be included in the conduit fill calculations, as they are the only wires carrying current at any given time. Counting all 3 wires for each three-way switch would overstate the actual number of current-carrying conductors present in the conduit. It is important to consult the National Electrical Code, or NEC, for guidance on conduit fill calculations. While the NEC does not specifically address the three-way switch scenario, the general principle of counting only current-carrying conductors applies to conduit fill calculations. NEC Section 352.4b states the number of conductors permitted in a single raceway shall not exceed the allowable percentage fill specified in Table 1 of Chapter 9. Since the 2 traveler wires are the only current-carrying conductors in each three-way switch configuration, only these should be counted towards the allowable percentage fill. To elaborate, let's consider the concept of current-carrying conductors. A current-carrying conductor is defined as a conductor that carries electrical current under normal operating conditions. In a three-way switch circuit, the common wire does not continuously carry current. Its function is solely to establish a connection depending on the position of the switches. Now let's delve deeper into conduit fill calculations. The purpose of these calculations is to ensure that the conduit is not overfilled with conductors, which can lead to overheating, insulation damage, and ultimately, electrical hazards. The NEC specifies the maximum allowable percentage fill for different types of conduits, and these values are found in Chapter 9, Table 1. These values depend on the number of conductors within the conduit. Understanding how to calculate the area of a conductor is necessary for conduit fill calculations. The area of a conductor is typically expressed in square inches. The NEC provides tables that list the cross-sectional area of different conductor sizes. Firstly, determine the size and type of conductors that will be installed in the conduit. Secondly, consult the NEC tables to find the cross-sectional area of each conductor. Thirdly, add up the cross-sectional areas of all the conductors to obtain the total conductor area. Fourthly, refer to NEC Chapter 9, Table 1 to determine the maximum allowable percentage fill for the type of conduit being used. Fifthly, calculate the allowable fill area of the conduit by multiplying the conduit's internal area by the allowable percentage fill. Sixthly, ensure that the total conductor area does not exceed the allowable fill area of the conduit. If the total conductor area exceeds the allowable fill area, a larger conduit size will be required. It is also important to consider derating factors for conductors in a conduit. When multiple current-carrying conductors are installed in a conduit, the ampacity of each conductor must be derated to account for the heat generated by the other conductors. The NEC specifies derating factors based on the number of current-carrying conductors in the conduit. These derating factors are found in NEC Table 310.15 cone. The ampacity of a conductor is the maximum amount of current that the conductor can safely carry. The ampacity of a conductor is determined by its size, insulation type, and temperature rating. The NEC provides tables that list the ampacities of different conductor sizes. It's also worth noting that there are specific rules for grounding conductors in conduits. Grounding conductors are used to provide a path for fault current to return to the source, helping to protect equipment and personnel from electrical shock hazards. The NEC specifies the minimum size of grounding conductors based on the size of the overcurrent protection device. Grounding conductors must be installed in accordance with NEC Article 250. When running multiple circuits in a single conduit, it is crucial to properly identify each circuit to avoid confusion and potential hazards. The NEC requires that each circuit be clearly identified at its termination points. This can be achieved through color coding, labeling, or tagging. Always use approved wiring methods and materials. The NEC specifies the types of wiring methods and materials that are permitted for different applications. It is crucial to use only approved materials that are listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories, or OL. Proper installation practices are essential for ensuring the safety and reliability of electrical systems. It is important to follow the NEC requirements and manufacturer's instructions when installing conductors, conduits, and other electrical components. Proper workmanship is critical for creating a safe and compliant electrical installation. When in doubt, always consult with a qualified electrical inspector or engineer. Electrical codes and standards can be complex, and it is essential to have a thorough understanding of these requirements to ensure a safe and compliant installation. Electrical inspections are conducted to verify that electrical installations comply with the NEC and other applicable codes and standards. Electrical inspectors have the authority to approve or reject electrical installations. It is important to address any deficiencies identified by the electrical inspector to ensure that the installation is approved. In conclusion, understanding how to calculate conduit fill for three-way switch wiring is crucial for ensuring a safe and compliant electrical installation. By counting only the 2 traveler wires for each three-way switch, adhering to NEC guidelines, and following proper installation practices, electrical professionals can avoid overfilling conduits, prevent electrical hazards, and create reliable electrical systems. Remember to always prioritize safety and consult with qualified professionals when needed. The safe and effective installation of electrical systems relies on accurate calculations, code compliance, and meticulous attention to detail. Let's consider a specific example. Imagine a 3/4-inch conduit run between 2 three-way switches. We need to determine how many conductors we can safely and legally install within that conduit. Firstly, we identify the conductors we need. We have 2 traveler wires for each three-way switch, plus a neutral wire and a grounding wire. That's a total of 5 conductors. Secondly, we consult NEC Chapter 9, Table 5 to determine the dimensions of the conductors. Let's assume we are using 12 American wire gauge, or AUG, THHN conductors. The table shows that the cross-sectional area of a 12 AWG THHN conductor is 0.133 square inches. Thirdly, we calculate the total area of the conductors. 5 conductors multiplied by 0.133 square inches per conductor equals 0.665 square inches. Fourthly, we consult NEC Chapter 9, Table 4 to determine the allowable fill for a 3/4-inch conduit. For more than 2 conductors, the allowable fill is 40%. Internal area of a 3/4-inch conduit is 0.533 square inches. Therefore, the allowable fill area is 0.4 times 0.533 square inches, which equals 0.2132 square inches. Fifthly, we compare the total conductor area to the allowable fill area. Our total conductor area of 0.665 square inches is less than the allowable fill area of 0.2132 square inches. Therefore, we can safely and legally install the 5 12 AWG THHN conductors in the 3/4-inch conduit. This example illustrates the process of calculating conduit fill. It is essential to follow this process carefully to ensure that the conduit is not overfilled. Overfilling a conduit can lead to overheating of the conductors, which can cause insulation damage and potentially lead to a fire. Now, let's discuss some common mistakes to avoid when calculating conduit fill. One common mistake is to forget to include the grounding conductor in the calculation. The grounding conductor is a current carrying conductor and must be included in the conduit fill calculation. Another common mistake is to use the wrong dimensions for the conductors. It is essential to consult the NEC tables to obtain the correct dimensions for the conductors being used. Another mistake is to use the wrong allowable fill percentage. The allowable fill percentage depends on the type of conduit and the number of conductors. It is essential to consult the NEC tables to determine the correct allowable fill percentage. Another mistake is to neglect to derate the ampacity of the conductors. When multiple current-carrying conductors are installed in a conduit, the ampacity of each conductor must be derated. Derating factors are found in NEC Table 310.15 Kern. By avoiding these common mistakes, electrical professionals can ensure that their conduit fill calculations are accurate and that their electrical installations are safe and compliant. Furthermore, understanding the broader context of electrical system design is helpful. This includes understanding concepts like voltage drop, short circuit current, and overcurrent protection. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC specifies the maximum allowable voltage drop for branch circuits and feeders. Short circuit current is the large current that flows during a short circuit fault. Short circuit current can damage equipment and cause fires. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical systems from short circuit current. The NEC specifies the requirements for overcurrent protection. Let's say you're running a long circuit to power a motor. You need to calculate the voltage drop to ensure that the motor receives adequate voltage. Firstly, determine the length of the circuit. Secondly, determine the current that the motor will draw. Thirdly, determine the resistance of the conductor per unit length. This information can be obtained from NEC Chapter 9, Table 8. Fourthly, calculate the voltage drop using Ohm's law. The voltage drop is equal to the current multiplied by the resistance. Fifthly, compare the calculated voltage drop to the maximum allowable voltage drop specified in the NEC. If the calculated voltage drop exceeds the maximum allowable voltage drop, you will need to increase the size of the conductor. Let's consider another scenario. You're installing a new panel board and need to determine the short circuit current at the panel board. Firstly, obtain the utilities available fault current at the service entrance. Secondly, determine the impedance of the service conductors and the transformer. Thirdly, calculate the short circuit current at the panel board using the following formula: short circuit current equals available fault current divided by the square root of the sum of the squares of the resistances and reactances. Fourthly, select overcurrent protection devices with an interrupting rating adequate to handle the calculated short circuit current. Understanding the relationship between these concepts is essential for designing safe and reliable electrical systems. Proper planning, accurate calculations, and adherence to the NEC are crucial for ensuring the safety and performance of electrical installations in commercial buildings. The role of technology in modern and electrical work should also be acknowledged. Digital multimeters, circuit tracers, and thermal imaging cameras are just a few examples of tools that enhance accuracy and efficiency. Digital multimeters provide precise measurements of voltage, current, and resistance, aiding in troubleshooting and verification. Circuit tracers help identify specific circuits within complex wiring systems, saving time and effort. Thermal imaging cameras detect temperature differences, enabling early detection of potential hotspots and preventing failures. Software programs for electrical design and calculation are also invaluable. These programs automate complex calculations, ensure code compliance, and generate detailed reports. Building Information Modeling, or BIM, software is increasingly used to create 3D models of electrical systems, facilitating coordination and collaboration among different trades. By embracing these technological advancements, electrical professionals can improve their productivity, reduce errors, and deliver higher quality work. Furthermore, continuous education and professional development are essential for staying up to date with the latest codes, standards, and technologies. The electrical industry is constantly evolving, and new products, techniques, and regulations are introduced regularly. Attending workshops, seminars, and online courses allows electrical professionals to expand their knowledge, enhance their skills, and maintain their competence. Certifications, such as those offered by the National Institute for Certification in Engineering Technologies, or NICIT, and the Independent Electrical Contractors, or IC, demonstrate a commitment to excellence and professionalism. By investing in their own education and training, electrical professionals can provide their customers with the best possible service and ensure the safety and reliability of electrical systems. Finally, the importance of teamwork and communication should not be overlooked. Electrical projects often involve multiple individuals and organizations, including architects, engineers, contractors, and inspectors. Effective communication and collaboration are essential for ensuring that projects are completed safely, on time, and within budget. Regular meetings, clear documentation, and open communication channels help to prevent misunderstandings and resolve issues promptly. By fostering a collaborative environment, electrical professionals can create successful projects and build strong relationships with their clients and colleagues. Remember, safety is always the top priority. Always follow lockout/tagout procedures before working on electrical equipment. Wear appropriate personal protective equipment, or PPE, such as safety glasses, gloves, and arc-rated clothing. Use insulated tools and equipment. Never work on energized circuits unless absolutely necessary. Be aware of your surroundings and potential hazards. If you are unsure about something, ask for help. By prioritizing safety, electrical professionals can protect themselves and others from injury and ensure that all electrical work is performed safely and responsibly.